None.
Hi, welcome back to the Network Plus Certification video series. I'm Mike Redmond, Master Trainer, here to help guide you through your successful journey of becoming a Network Plus certified technician. We're going to walk through a wide variety of topics, starting with basic network concepts all the way through network management and security. In this segment, we're going to talk about network models. I'll describe how models such as the OSI 7-layer model and the TCP/IP 4-layer model help technicians understand and troubleshoot networks. I'll explain the major functions of network hardware and the OSI 7-layer model, as well as describe the major functions of networks with the TCP/IP model. I'll help you compare and contrast the difference between TCP and UDP and define and exemplify some frame, packets, segments, datagrams, and ports. So as we begin our discussion, you need to understand that this chapter is the cornerstone for everything else that we're going to talk about over the course of this certification series. It all starts with the two different models. We're going to start with the OSI 7-layer model. This provides a powerful tool for diagnosis. It's a common language, if you will, between network administrators to describe networks and how they're connecting and communicating. Then we have the TCP/IP model. It's just another model that we will describe in depth a bit later on. Understand that it describes the actual de facto protocol of the internet. It's how the internet works. Each layer of the TCP/IP model, you may often see it referred to as the DoD model, maps directly to the OSI model very well. So first, let's start with the model concept. In general, a model has a look and feel of the actual thing. So we use these models to help conceptualize and troubleshoot our networks. With that understanding, we'll then go into the OSI 7-layer model and the TCP/IP model to see how they help clarify network architectures for technicians. The best way to learn the OSI and TCP/IP models is to see them in action. So let's talk about models. What is a model? We have lots of them around us: computer models that predict the weather, plastic model airplanes, fashion models. They're all models. The model has the major functions of the real item. So there are different model types, especially when we start talking about networking. These two models, the OSI layer model and the TCP/IP layer model, these models act as guidelines and break down how a network functions into discrete parts called layers. All models are simplified representations of the real thing. The main benefit is that now we have a tool that we can use to provide powerful mental diagnosis to problems that help zero in on a solution. They provide us a common language to describe our networks. It's a way for us to communicate with each other about the functions of the network. So with the OSI 7-layer model, it was originally proposed by the International Organization for Standards. It works for almost every type of network. Each layer is well defined with a function and a related protocol. So here is the OSI 7-layer model: physical layer, data link, network, transport, session, presentation, and application. So let's look at each of these layers a little more in depth. starting with layer 1. This is your physical layer. This is where your cabling and your actual radio waves or carrier signal waves reside. Hardware devices like hubs and your network interface, they all live in the physical layer. That's the first thing that you can touch. They connect to layer 2, the data link layer. That's where your switches live. So, just to try to think it through, let's say that we have a worker that has just completed a new employee handbook. She wants to transfer that Word document to another worker for her to review before sending it to the boss. Janelle and Donna are here hard at work with a simple problem. Networking is how we fix that. So there are multiple things that she could do. She could copy them to a flash drive, for instance, and walk it over. We call that sneaker netting. It is a form of networking. Or she can transfer the file using some sort of electronic medium. That would be the network. So at its heart, at the very base of everything, it starts, like I said, at the physical layer. This is the personality of the network, if you will. It's your cabling. There are several different kinds of cables that you're going to need to be familiar with to successfully navigate the Network Plus exam. We're going to start with the UTP cable, probably absolutely the most common type of cabling in modern networks. UTP is unshielded twisted pair. Next, physical equipment like a hub. Each computer system has a cable leading to a device. That device often will be called a hub. The hub sends the data received from any individual system, and then all other systems connected to that hub receive that data. It's a large broadcast domain. So now, as Donna prepares to hit send, we've taken care of the physical layer. We understand the medium and media that it will travel. Next, we need to begin moving up the OSI model. This would be layer 2. This is where switching happens, your switches and bridges and your network interface cards. That is a layer 2 device. It provides for physical addressing of machines. Here's a look at a typical NIC. This is the device that your network cables are plugged into. The cable runs from the NIC in the PC to usually a jack on the wall. The cables run through the walls to a closet, and that closet connects to usually a switch or a hub. So understand that your NIC, like I said, is your physical address. Each system on a network must have a unique identifier. We call that the MAC address, or the media access control. It's a unique address burned into the ROM chip of the network card itself. Each MAC address is 12 hexadecimal characters, or 48 bits in length. So if you want to, for instance, view your MAC address on a Windows PC, it's as simple as opening up the command line and typing ipconfig space \all. That will give you, along with many other pieces of configuration information, you can view your MAC address of your machine. So these MAC addresses, as I indicated, are unique to every machine. The Institute of Electrical and Electronics Engineers, or IEEE, controls and issues MAC addresses to hardware manufacturers. This standard is also called MAC48 or EUI48, Extended Unique Identifier. Each hexadecimal character represents 4 bits. It takes 12 hex characters to represent the entire 48, and it's broken up into two halves. The first 6 digits are unique and specific to a manufacturer. The last 6 digits are going to be the serial number for that device. There are no two same Mac devices in the world. So now we have our physical layer, and we're starting to understand layer 2. We're about ready to put the data on the wire. First, we need to understand how our data moves. It's in a digital format. If I were to put an electronic stream of data through an oscilloscope, it would be choppy and blocked up, kind of like this. However, this needs to be translated by your computer. And understand, your computer only understands zeros and ones. So the same oscilloscope data now to your computer looks like this. Each up wave tells the computer that the bit is turned on. A down wave, the bit is turned off. So 1 0 1 0 1 1 1 0 1 1 matches the waves of the oscilloscope. So say hi to our friend Nick. Nick now needs to send data across the network. So Nick has a job to do, and as we continue, we're going to help Nick out. It all starts with a frame. Frames are made up of fields that contain information. For instance, frames contain the recipient's MAC address, the sender's MAC address, the data itself, and a small piece at the end called the FCS, the frame check sequence. This is for error checking to make sure that the data gets there in one piece. You can think of this frame as a canister, much like you'll use at your bank drive-thru. It contains all of this information that we now need to put on the wire. Different networks use different size frames. Many frames hold about 1,500 bytes of data. The sending software breaks up large amounts of data into those smaller chunks. The receiving station then puts the chunks back together in proper order. So when connected to the hub, all devices on the network see the frame, but only the device that it is addressed to will process it. So every frame is received by every NIC. Remember, I explained it was a large broadcast domain. We'll get into the broadcast domains a little later. However, understand at this point, all we're trying to do is get our data from one machine to the next. That is what the MAC address helps us do. So since the cable is shared, only one system can speak at a time. It's only polite to take turns. Processors are used to keep two NICs from talking at the same time. So now we're beginning to understand. This is how computers take turns on the line to make sure that they don't interfere with another individual's communications. So usually two devices have talked before, so the destination MAC addresses are already known. However, if the MAC address is not known, a broadcast message is sent out over the network. It's also represented in all hexadecimal characters, looking like a MAC address, because remember, every machine needs to be speaking a common language, and at this layer, this is the only language that they know. So the broadcast address is formed by hexadecimal characters. So now Nick can begin the process of doing his job. He has his frame, he has his data, he's begun to put it all together. Now he needs to receive that command to send the data, and that is when Nick actually begins building the frame, when you hit send. Now, when the frame is received by the receiving computer, that receiving station checks the FCS. If the value matches, then the NIC sends the data portion to the network operating system for further processing. If the values don't match, the frame has errors and must be resent. So I indicated that we were dealing with a 7-layer model. That's mostly true. However, layer 2 is broken out into 2 sublayers: the media access control layer, the MAC, and the logical link control. That is the helper, if you were, to get to the next layer where the logic of the network lives. This is the only layer that's broken out into those 2 sublayers, so don't worry about the rest. This is the only one that you'll need to remember. Next, let's continue watching our data flow across the network. We're now at layer 3. This is the network layer. This is where routers and multi-layer switches live. This is the layer that handles logical addressing. Containers, called packets, are what reside in this layer. We're no longer necessarily within frames. This is where you find TCP and UDP. These are the protocols that the network layer understands. There are others, but these 2 are the most dominant. This is where we find the TCP/IP suite, made up of TCP, the transmission control protocol, and IP, the internet protocol. Like I said, there are some others, but those really by and large are just not used anymore. So IP technology, now we need to understand a different way of counting numbers. We're no longer counting numbers in hexadecimal format. Now they've changed to dotted decimal notation. They range from 0 to 255. You've probably seen an IP address that looks like this: 192.168.100.123. This is a logical address for the machine. It is away from the physical addressing that we have done at layer 2. This is the way we break out our larger networks into subnets. So let's talk about these devices called routers. Routers are used to chop up large networks into smaller networks. Routers forward packets by their logical address. That's where we find, again, the IP addressing. An IP router, which is the most common, forwards those IP packets. This is only being performed at layer 3, the network layer. So a common IP packet looks like this: destination IP, the source IP, and the actual data that it's carrying. So far, NIC seems to be doing a pretty good job. So now we have frames and packets within those frames. Network software creates a packet that contains the sending and receiving IP addresses along with all that data. You need a couple more pieces of information, like the data type and the packet count, but we'll get into that again later. So now we have our packet that is enclosed within the frame that contains the sending and receiving MAC addresses, as well as the IP information. This is how we connect to the network or the internet. The router connects a local network to the internet. The local hub or switch is in turn connected to the router, and the router is connected to the internet through a cable or a phone line. The cable or phone line use a different kind of frame, so the router strips the frame and creates a new one. So now we have our router doing what routers do best. The router replaces the MAC address with the type of address used by the cable or phone company. The frame uses the IP address to guide it to the receiving station. Once it arrives, the receiving router strips off the cable or phone company's special frame and adds the MAC address of the receiving station. Then that NIC will strip off the MAC header and hands the frame off to the network operating system. Next, let's talk about layer 4, the transport layer. This is where assembly and disassembly begin to happen. Most data is much larger than a single frame. A network protocol is needed to chop up the data into smaller packets and give each one a sequence number. We've talked about that. These sequence numbers are used by the receiving system to put the packets back in order. Remember, the internet is wide open space. Every packet knows where it needs to go, but your data doesn't necessarily travel in a sequential order. It just knows it needs to get to its destination. It'll be reassembled once it arrives. This is a little like how UPS delivers boxes. Lots of boxes coming from lots of different places, but only to one single address. That is how the transport layer works. Primary protocols that we deal with in the transport layer are, again, TCP, UDP, and SPX. So TCP, Transmission Control Protocol, is a connection-oriented protocol. It's built on a foundation of what's called the three-way handshake. We'll discuss that a little later as well. They are SYN and ACK packets designed to verify end-to-end connectivity. It verifies that packet delivery and resends if a packet is dropped. These synchronized and acknowledgement packets, they travel through specific ports, ranging from 1 to 65,535. Then we have UDP, or the User Datagram Protocol. This is a connection-less oriented protocol. It's a best effort. There's no connection or packet delivery verification. So within layer 4, we have specific services that happen. Segments, datagrams, assembly and disassembly, reliable or unreliable delivery of your data and information, error correction and flow control. The transport layer is also where the initialization of requests for packets that weren't received in good order comes from. Next, the session layer, layer 5. Understand that it is possible to have a conversation with more than one person. For instance, you could be on the phone talking to one person while sending an email to another and perhaps sending a text message to a friend, all simultaneously happening together. This session layer is what manages all those different types of communications. The software that handles these processes is called the session software. It only works at layer 5. This is where synchronization begins to happen. The session establishment, tracking, and naming. It initializes sessions, accepts incoming sessions, opens and closes existing sessions. This is also where we begin the practice of security and name recognition and auditing. Some of the layer 5 protocols are NetBIOS and RPC, remote procedure calls, happen at layer 5. Next, we have layer 6. This is the presentation layer. Tasks are solved here at this layer. Macs and PCs, for instance, have not always talked the same language. However, in an effort to coexist, we had to figure out how to allow someone with a PC to communicate with someone with a Mac. So at layer 6, the presentation layer, we've standardized the formats to allow every different type of operating system to be able to seamlessly exchange data. This is where you'll find protocols such as JPEG, TIFF, and GIF files. This is also where TLS and SSL live. We're handling data encryption and decryption in layer 6. And finally, layer 7, the application layer protocol. Users use the application layer network application to exchange data on the network. This is where, for instance, Windows Vista and Windows 7 live. Web browsers, Outlook, all live in the application layer. It is the layer that is interacted with by the users. This is where we handle our resource sharing and directory services like Active Directory. This is where our email is handled, SMTP, the Simple Mail Transport Protocol. So now let's talk about the 4-layer model, the DoD or TCP/IP model. Understanding that the OSI model was developed due to a need to standardize hundreds of different protocols made by different manufacturers. In the end, one protocol suite really won out. It's now the de facto standard for the internet. It's TCP/IP. TCP/IP is both a protocol and a model. The TCP/IP model layers map to the corresponding OSI model layers. They perform the same functions and use the same technology, protocols, services, and devices. Some layers map directly to the corresponding layers, while other ones have more of a correlation. So TCP/IP does not have a standards body like the OSI model does. This is the result of many interpretations and variations within the models. Variations used in the exam is the most popular used by major manufacturers like Microsoft and Cisco. However, this variation uses 4 standard layers: the link network interface, the internet layer, the transport layer, and the application layer. The application layer, much like layer 1 in the OSI model, corresponds to the layers 1 and 2. It handles the physical elements of the network, cabling, hubs, physical addresses, or your MAC address. Software and higher level protocols work in the higher level layers of the TCP/IP stack. This is also where you'll find your frames. However, in the TCP/IP model, they are referred to as PDUs, or protocol data units. Next, we have layer 2. This is the internet layer. It deals with any device or application that uses IP protocols and IP addressing, as well as routing. Routers function in this layer of this model. This maps directly to layer 3 of the OSI model. Now, the PDUs at this layer are called packets. Layer 3 is the transport layer. This layer maps to the OSI transport layer as well as the session layer and some of the application layer. It uses 2 protocols, TCP and UDP, and provides both connection-oriented and connection-less communications, just like the other model. Now, the PDUs are segments with TCP and datagrams with UDP. So we've discussed how TCP provides a connection-oriented communication. It's important to understand what types of applications you're talking about. You're talking about HTTP and POP, web, and email. These all require good, established, reliable communication. TCP flows a prescribed set of procedures to establish and keep a good connection. It synchronizes the session between transmitting and receiving hosts. UDP, the connection-less communication, used by some of the upper layer protocols that don't require reliable, verified connections. UDP sends data without waiting to see if the receiving system is even ready to receive it. Protocols and applications like streaming audio and visual and DNS queries and DHCP broadcasts. So each TCP segment contains a header of information, such as the source and destination port, the sequence, the acknowledgement numbers, and flags to ensure that connections are established and verified. Data follows then that TCP header information. With UDP datagrams, they only have 4 header fields. No mechanisms are built in to establish, verify, or track connections. And after those 4 fields, your data will follow that UDP header information. And now we have the top layer of the TCP/IP model. It's the application layer. This maps directly to the top 3 layers of the OSI model. It contains the applications that you're probably most familiar with, like DNS, DHCP, and HTTP. It allows presentation layer formats such as MIME or email and application layer APIs. So with each layer of both the OSI and the TCP/IP model, we deal with a method called encapsulation. These models encapsulate data by adding headers in front of the data to be able to pass it on up and down each of these models stack. The data is called or known by different names as it travels through each layer. So these names are called protocol data units. You should know and understand the concept of encapsulation because you will begin to hear it more and more as we discuss deeper and deeper networking concepts. So one more important set of tips for you. You absolutely must memorize the OSI and the TCP/IP layers. A simple mnemonic for the OSI layers are all people seem to need data processing. That'll help you keep them in order from 1 to 7. Remember, only the data link layer is the layer that is broken up into 2 sub-layers, the media access control and the logical link layer. And remember at which layer encapsulation happens. All of them must encapsulate going up and down the stacks. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time. That